Hello everyone, my name is Partho Das, Assistant Professor, Department of Electrical Engineering, JS College of Engineering, West Bengal, India. First of all, welcome to my class. So as you can see, today's topic is the two reaction theory of saline pole machine. So let us start with my presentation. So yes, what is the theory of the two reaction saline pole machine have regarding the two reaction theory? So in this, it is known that in case of non-saline pole type alternators, the air gap is uniform. Due to uniform air gap, field fluxes as well as armature flux vary sinusoidally in the air gap. In non-saline pole alternators, air gap length is constant and reactance is also constant. Due to this, the MMF of the armature and field act upon the same magnetic circuit all the time, hence can be added vectorically. That means what? So when we have discussed the construction of alternators, there we have seen the two types of alternators are there. One is the saline pole alternators and second one is cylindrical. In case of cylindrical alternators, as the air gap is as the air gap is uniform, so whatever fluxes are produced over here, that may be field flux or may be armature flux, that varies sinusoidally in the air gap. But in case of saline pole alternators, the length of the air gap is not uniform, it varies, and as the length of the air gap is not uniform, its reluctance also varies. Hence the armature flux and the field flux cannot be vary sinusoidally in the air gap. The reluctances of the magnetic circuit on which EMF acts are different in case of saline pole alternators, because the length, the distance between the poles and the area adjacent the poles are not equal in length, so the air gap is not uniform. So today we are going to derive what is the how we can find out the EMF and MMF values in the air gap. So as the uniforms, the air gap is not uniform. Yes. So Professor Andre Brondel has invented this method that is known as the two reaction theory. So where the saline pole is divided into two sections. Okay, so let us see what is there in the particular theory. So according to this theory, the armature MMF can be divided into two components. Are components along the pole axis is called the direct axis, and components acting in the right angles to the pole axis is known as the quadrature axis. Again I am telling that components acting along the pole axis is known as the direct axis. Components components acting at right angles to the pole axis is called quadrature axis. The component acting along direct axis can be magnetized or demagnetized. The components acting along quadrature axis is cross magnetizing. This component produces the effect of different kinds. So we are dividing this saline pole into two different components. One is axis on the axis of pole axis, that is known as the direct axis, and there is a right angle to the pole axis, that is known as the quadrature axis. So let us see. Yes. So in this particular diagram, so left hand side diagram and right hand side diagram, there are two diagrams is there. In the left hand side diagram, as we can see, the saline pole tips are we can see there. So there the reluctance is very less, so the maximum flux will try to flow there, and that is known as the direct axis. And so follow my pointer, this is the direct axis. Okay, and this one, here we have the, follow my pointer, here we have the pole tips. So here is the air gap is very high, as we can see. So there is a huge distance between this, so that is known as the quadrature axis. Okay, so that is not uniform. It's when there is a so we can say that the pole the air gap is not uniform, that when the poles direct axis we are considering, the air gap is very small. When we are considering the quadrature axis, the um, air gap is very high. The reluctance offered to the mmf wave is lowest when it is aligned with the field pole axis. Yes, definitely, as the air gap is very less, and this axis is called as direct axis of pole, that is the D axis. The reluctance offered is highest when the mmf wave is oriented at 90 degree to the field pole axis, which is called quadrature axis or the Q axis. The air gap is least in the center of the poles and progressively increases on moving away from the center. Due to such shape of the pole shoes, the field winding wound on Salient pole produces a mmf wave which is nearly sinusoidal, and it always acts along the pole axis, which is direct axis. Okay, so next we will see next we will going to consider some components by which we are going to derive the expressions for this two reaction theory. So what are the assumptions we have to make, what are the values we have to assume? So let us see that what are the values we are going to consider over here. Let if be the mmf wave produced by field winding, then it always acts along the direct axis. This mmf is responsible for produce an excitation emf ef, which lacks this ff by an angle 90 degree, obviously. So we know that emf is lags behind the flux by an angle, mmf by an angle 90 degree. When armature current carries it produce when armature carries current, it produces its own mmf wave, that is FAR. AR is for the armature reaction. This can be resolved into two components, again one acting across the D axis, that is the cross magnetizing effect. Similarly, armature reaction IA also has its two components. What are the components? One along the direct axis, one along the quadrature axis. So that means in the armature section, this mmf has two components, at the same time current has two components. So let us see what are the mmf components we have, what are the armature current components we have. So if AR, that has the armature mmf that has two components, FD and FQ. FD is the components along direct axis and FQ is the components along quadrature axis. Like that way, current has two components, one is the ID and IQ. ID is a component along direct axis and IQ is a component along quadrature axis. Yes. So the position of this FAR, the mmf of armature reaction, this FD and FQ in space are shown in the figure below. So as we can see that there is follow my pointer. So in this particular presentation, in this particular diagram, so this is the D axis and shipment of 90 degrees. So this is the Q axis. Okay, and this is the position of maximum current, this R and R. There is a positive, there is a negative. The instant chosen to show this position in such that the current in the phase R is maximum positive and is lagging EF by an angle xi. Okay, so next, the armature current lags the generated EMF by angle xi. It can be observed that this FD produced the direct axis MMF is produced by the direct axis current, which is at 90 degree to EF, while this FQ, that is the quadrature axis mmf, is produced by quadrature axis current IQ, which is in phase with this IF. Obviously, if it is if D is 90 degree shifted from this IF, obviously this FQ will be in axis of this EF. Okay, so the flux components of QR, which are a phi D and phi Q along the direct and quadrature axis respectively, are also seen in the diagram. So what we can see over here, so just first see the what is there in this particular diagram. So in this axis we have the phi Q, okay, and that axis we have, this is the quadrature axis and this is the direct axis. So over the direct axis what we have, so we have the um, phi d and phi fd, and here the below section always we have that id, fd and phi d, and this is the quadrature axis. Obviously over this we have the components q, q, fq, iq, and as we have discussed that in the along the uh, FQ axis we have the EF. So as we can see this EF, follow my pointer, this EF in the axis of this FQ. Okay, so as it is a 90-degree shifted from this one, so this is the resultant. Okay, this one is the resultant as we can see. Oh, and this angle is a xi over here. So it can be denoted that the reactance offered by flux along direct axis is less than the reactance offered to the flux along the quadrature axis. Due to this, the flux QR is no longer along FR or IA, depending upon the reluctances offered along the direct and quadrature axis. The flux phi AR lags behind IA. So now we know that the armature reaction flux phi AR has two components. Again, along the direct axis there is a phi D, along the quadrature axis is a phi Q. These fluxes are proportional to the respective MMF magnitudes and the permeance of the flux path oriented along the respective axis. So now we can write down the phi equation. So phi equation is equal to the phi d is equal to pd into fd, where this pd is the permeance along the direct axis, and what is phi d? That is the MMF along the direct axis. Permeance is the reciprocal of the reluctance, obviously, and indicates ease with the which can control around the path. But FD, okay. So now what is FD again? FD is this MMF in the direct axis. What is again? They can be given by KAR into ID, where ID is the direct current along the direct axis, and KR is the armature reaction coefficient. So like this way we can find out the FD in terms of phi d is equal to pd, that is the permeance, and fd can be replaced by kd kar into id. So like similarly we can in the quadrature axis also we can find out the flux value. So phi q is equal to pq kr into iq. Yes, as the reluctances along direct axis is less than that along the quadrature axis, the permeance PD along the direct axis is more than the quadrature axis. Obviously, the reluctance along the as the reluctance of the direct axis is less than the quadrature axis, the permeance in the direct axis obviously more than the quadrature axis. That means the ability to generate the flux, ability to the flow of the MF, the flow of the flux, that be higher. So let ED and EQ be the induced EMF due to the fluxes. So that means when the fluxes are flowing, that what are the fluxes? Phi d and phi q, two fluxes are in the direct axis, there is a flux, in the quadrature axis there are two flux. So due to that two EMFs we are assuming, that is ED and EQ. ED is the direct axis EMF, EQ is the quadrature axis EMF. Now ED lags phi d by 90 degree, while ED lags phi QQ by 90 degree. So we can write down ED is equal to KE into phi d at an angle minus 90 degree. So if we change that to polar to rectangular format, so we can write down minus j ke phi d, where similarly EQ is equal to ke phi q at an angle 90 degree is equal to minus j ke phi q, where K is the EMF constant of armature winding. Okay, so we can know, we can write down that. So what is the resultant EMF? That is a phasor sum of EF, ED and EQ. So we have written that ER is equal to, so all a vector summation, ER is equal to EF plus ED plus EQ. So now we know the values of ED and EQ from the above equation. So we will place that over there, EF minus JKE phi d minus JKE phi q. So that is, these are the equation. Okay, so now again we know the value of this phi. So phi d and phi q values are already we have expressed. So now we can put that value in this particular equation. So now the equation become er is equal to ef minus j ke pd kr uh, into id minus j ke in the quadrature axis element, that is ke pd kr into iq. Okay, so now we are considering that XARD is the equivalent resistance corresponding to the D axis of armature reaction. So it is equal to the KE into PD into KAR. At the same time, the quadrature axis equivalent reactance, we are considering that equivalent reactance corresponding to Q axis of armature reaction, that is given by XARQ. So it is equal to the Ke into Pq into Kar. So now replacing that, instead of Ke Pd Ar, we are replacing the Xard. In place of Ke Pq Kar in the last component of the equation, Er equation, we are replacing that Xarq. So we are now simplifying that equation. Yes, so for a realistic alternator, we know that the voltage equation is given by this one. Er is equal to Vt plus IARA, the drop, plus IXL into IA. Okay, where this Vt is the terminal voltage and it is XL is a leakage reactance, we know that. And armature current is given by, it has two components already we have discussed, that is ID and IQ. And Er is equal to Vt, as so the above equation in this particular slide, the Vt plus IARA plus IXL into IA, that can be rewritten like this way, as this IA armature current is equal to the summation of two components, direct axis current and the quadrature axis current. So the ER can be rewritten as Vt, all other vector components, Vt plus IARA plus XL ID plus XL IQ, substituting the expression for ER. So if we do that, so in the Vt, if we just substituting the values of Er in this equation, we will get what we will get. We will get that Vt plus IARA plus XL ID into plus XL into IQ is equal to EF minus J XRD ID minus uh, J into XAQ IQ. EF is equal to Vt plus IARA plus, just we are simplifying the equation, taking the real part one side and taking the complex part in the one side. So if we do that, so we can say that uh, see, it is very simple, very much simplifying, that EF is equal to Vt plus IARA plus J into XL plus XARD into ID, that is the direct axis components, and plus J XL plus XARQ into IQ. So instead of those, we are rewriting in the next line, that is EF is equal to Vt plus IARA plus JXDID plus JXQIQ. So this is only the mathematical calculation, though that's why I'm just telling you what are the steps it is following. So you have to just when you are practicing at home, so what you will do, you will first take the concept, so why it has two components, then just you have to think about from the mmf to flux to emf equation, how they are changing step by steps. Everything I have written over there, so step by step you just practice it in your copy. It will be very easy to remember, to understand. Okay, so where this we are simplifying that equation, where we are written that xd is equal to xl plus xard, xq is equal to xl plus xard xarq. Okay, so the what is the observation we have made from this, that it can be seen from the above equation that the terminal voltage Vt is nothing but the voltage left after deducting the ohmic drop IARA, the reactance drop ID XD in quadrature with ID, and the reactance drop IQ and XQ in quadrature with ID from the total EMF EF. Okay, that means in the direct axis whatever drops are there, in the quadrature axis whatever drops are there, if we subtract that from the generated EMF, the rest amount of voltage is appearing in the terminal. So the phasor diagram corresponding to the equation can be shown in the figure 1. The current I lacks terminal voltage Vt by phi. Then add IARA in phase with IA to Vt. The drop ID XD leads ID by 90 degree, as it is purely reactive circuit lacks current voltage by 90 degree. Okay, so let us come to the phasor diagrams. Now we will see the how the phasor diagrams are drawn. In the phasor diagram shown in the figure below, the angles I and delta are not known, though Vt, I and phi values are known. Hence, the location of EF is also unknown. The components of IA, ID and IQ cannot be determined, which are required to sketch the phasor diagram. So what is there? So let us check what is there. So this is the ID axis, direct axis. This is the quadrature axis, definitely. Okay, and this is the IA, armature current. This is the terminal voltage. So from between, see this, between this IA and VT there is an angle, that is the power factor angle. Then we have the drops. What are the drops? Resistance drop is there, reactance drop is there, and reactance drops can be divided into two sections. One is the uh, direct axis, one is the second quadrature axis. So the previously we have discussed the um, phasor diagram. Here with there we have considered only the resistance and the resistance drop and the synchronous reactance drop. Now here this reactance again can be divided into two. One is the direct axis reactance and the quadrature axis reactance. So that's why, see this one, over the voltage terminals we have the IARA drop parallel to this IA. Then from there we have a shipment, as it from the current the voltage is leading, that is XD IQ, XD ID XD, and from there IQ and XQ axis is 90 degree shifted. So there from XD axis it is 90 degree shifted, and from there the top of this IQ XQ we have drawn the resultant, that is EF. Okay, so these are the phasor diagrams. So like this way different phasor diagrams can be drawn. So this is the so components of IA. So phasor addition of the components of picture 1, this above picture is representing the what are the components we have in armature current. So it has also components in the direct axis, in the quadrature axis. So here the next one is a phasor diagram of component drops. So what are the drops is appearing? So here we are trying to represent different waveforms that we are using over here. So um, different phasor diagrams are representing the what are the characteristics we have and how they are leading lagging with each other. So those phasor diagrams are represented over here. Just carefully view the phasor diagrams, you will able to understand what are those. So here also some phasors we are representing over here. So this is a phasor diagram of Salient pole alternators. So I think this is it is enough for your understanding, that is what is two reaction theory of this Salient pole machine. So basically the thing is that when there is a non-uniform air gap, so that non-uniform air gap can be divided into two sections. One is the direct axis along the pole axis, and what is the quadrature axis, it is 90 degree from the pole axis. And respect to that we have to think of the MMF, the fluxes and currents, and then we have EMF and resultant EMF, then we can find out the phasors. So this is all for today. Thank you.